In this video, we're going to compute the flux of a vector field across some surface. So in this video, we're just going to have the formula that we came up with previously, and we're going to try to evaluate it in this specific example. So the first thing I want to do is investigate what this surface actually is. This is the surface z is 1 minus x squared minus y squared, and z is also greater than or equal to 0. So graphically, what this looks like is a surface that is just a parabola. In the xy plane, as in when you substitute in z equal to 0, you just get the equation of a circle, 1 is equal to x squared plus y squared, and then it looks like a parabola over top of that. Now the only thing I have to specify, which I haven't described in the problem itself, is which way am I orienting this particular surface. So I'm going to assert for you that I am orienting it with outward normals, outward from the perspective of starting at the origin and going out through the surface this way. I could have asked, similarly, what was the flux going the opposite direction, but I'm going to specify this is the interpretation that I mean. So that's the surface. And then I also have a field here, which is the field F is x in the I hat, y in the j hat, and z in the k hat. And this vector field is actually one that we've seen before. This is a vector field that just goes straight out at any point. For example, we had previously called that vector a normal vector, but it also happens to be that the field vector is exactly parallel to this normal vector. So I have that sticking straight out in every single spot. Okay, so that's most of my setup. And then finally, what's the formula I'm going to use? Well, the formula that I will use that we spent some time deriving in our previous video is that the flux is the double integral, and now I have a bit of a choice because it depends on whether I want to consider the flux formula for a surface described parametrically, or explicitly, or implicitly. Well, in this case, my surface actually is described explicitly. Z is 1 minus x squared minus y squared. So I could use that. But the region that is imposed by z equal to 0 is a circle down in the xy plane. And this is going to be described very nicely parametrically. It's easy to describe a circle. And so because of that boundary condition, I'm going to use the parametric form, in which case the integral is f dotted with Ru cross Rv du dv. That's the formula that we have to describe the flux. And so really what my goal is to figure out, well, what is this position function in terms of the parameters u and v? What parameters should I use? If I know that, then I can more or less plug into this formula. As noted, in the xy plane, we're going to have this circular region. And so r and theta, inspired by polar coordinates, is our natural choice for parameters. So if I do that, then my r of little r and theta, so I've got one a vector, position vector, and then the other, the parameter r, is going to be given by, well, the x component is r cosine of theta. The y component is r sine of theta. And then let's think about the z component. I know that z is 1 minus x squared minus y squared. So in our theta coordinates, x squared plus y squared is r squared. So this is 1 minus r squared. So that's the surface. But I also have this field, which was x comma y comma z. Now, it turns out that the choice of field that I have here, f being x, y, z, that just gives you the position. It's the same thing as the r. There really is no difference. So this is just going to be r cosine of theta, r sine of theta, and 1 minus r squared, exactly the same as what we just had. And this is just a coincidence by the specific choice. Generally, if it was some other function of x, y, and z, you'd just plug in the r cos theta, the r sine theta, and the 1 minus r squared into whatever those functions were going to be. So that's the r and the f, but I do have to compute the partial derivative still and plug them into my formula, which is the cross product formula. Okay, so now I want to compute out r, the partial with respect to r, crossed r theta, the partial with respect to theta. This is defined to be a determinant of this sort of funky matrix here, and I had to do some partials in my head here. So the second row is the partial with respect to r. So that's going to be cos theta, sine theta, and minus 2r. The derivative of 1 minus r squared is minus 2r. Then for the third line, this is the partial with respect to theta. So I'm going to take a minus r sine of theta and r cosine of theta, and then just a 0 in that third component. This is straightforward to compute. So in the I hat, I'm going to have minus 2r squared cosine of theta. All right, then I have a minus j hat. It looks like a minus, 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 which is 3 minuses, makes 1 minus, and I have 1 there, 4 minuses, lots of minuses. Anyways, of 2r squared sine of theta. And then finally, plus a k hat times r co-squared plus r sine squared, which is just plus r. So plus r times k hat. Now, that was the cross product, which was one of the two things in my dot product of my original formula. The other was the field itself. So if I wanted to compute out the flux, which was the double integral of the f dotted with the rr cross r theta, dr d theta, well, I have to take the dot product of these two things that I've computed. Okay, so let's see if we can do that. I'll just put a big R down here for region because I haven't figured out my limits of integration yet. I'll do that shortly. Anyways, this is a double integral. And then my f dot dr, well, it's sort of the first component there and the first component there multiplied together. So I have a 2, looks like r cubed co-squared theta. Then the second component squared looks like a 2r cubed sine squared theta. Oh, I always love those co-squareds and sine squareds coming together that way. And then finally comparing the third components is going to be a plus r minus r cubed. And then all of this dr d theta. Here I'll put in some brackets. So that's the expression that I'm interested in focusing on. Now I want to think about my limits of integration here. So first of all, it was the circle of radius 1. Remember we had this parabola over z equal to 0, and z equal to 0 you got x squared plus y squared equal to 1. So what it is the radius is between 0 and 1, and the theta between 0 and 2 pi. I'll slip that in there. Now I think I can do quite a bit of simplification here. So I have a co-squared and a sine squared. That's going to come together. That's going to leave me with 2r cubed. But I also have another term with r cubed, which is a minus r cubed. So I think that the answer is 0 up to 2 pi, 0 up to 1, r plus r cubed dr d theta. Which, well, the outer integral, there's no thetas involved, so I'll just put the 2 pi out in front of this. R is going to become r squared over 2 between 1 and 0, which is 1/2. R cubed is going to become r to the 4th over 4 between 0 and 1 is a quarter, which gives me 3/4 times 2 pi. In other words, 3 pi divided by 2, final answer. All right, so we have managed to compute the flux of the original vector field across this surface via parameterizing it and plugging it into our formula for flux.